In a museum vault, there is an iron axe head forged around the year 1200, more than 800 years old, its surface darkened by time and covered in a stable patina that formed through centuries of exposure to air, moisture, and use. There is no deep pitting or structural decay, and the metal beneath the surface remains dense, coherent, and strong, still capable of doing the work it was made for. Now compare it to a steel axe purchased 2 years ago and stored in a garden shed, its surface already marked by orange corrosion, with rust spreading unevenly, creeping along edges and sinking into microscopic imperfections. Within a few more years, the corrosion will weaken the metal to the point that the tool is discarded. This contrast should not exist. Tools made with primitive furnaces, charcoal fires and hand-powered bellows should not outlast tools produced by modern industrial metallurgy, and yet they do. This difference is not an accident. It is the result of chemistry, manufacturing process, and economic priorities. Medieval iron lasted because it was made under conditions that preserved internal structures that modern production deliberately removes. Modern steel fails sooner because it is optimized for speed, uniformity, and cost, rather than longevity. The difference is not ignorance. It is a difference in what is valued, what is measured, and what is rewarded. To understand why medieval iron resisted corrosion so effectively, it is first necessary to understand what modern steel actually is. Most tools sold today are made from mild steel, a material that typically contains approximately 0.25% carbon. During modern refining, slag and phosphorus are removed almost entirely. From an industrial perspective, this is considered progress. Slag-free steel rolls easily, phosphorus-free steel welds predictably, and the metal behaves consistently under automated processes. These properties allow manufacturers to produce large quantities of identical products quickly and cheaply. Medieval wrought iron was fundamentally different. It contained significantly less carbon, often around 0.05%, but it retained slag from the smelting process as well as naturally occurring phosphorus from the ore itself. These elements were not intentionally added. They remained because early smelting technologies were incapable of removing them. When modern steel corrodes, the process is aggressive and directional. Moisture and oxygen react at the surface, forming rust that is porous and unstable. Because this rust traps water, it accelerates further corrosion. Over time, the reaction follows microscopic grain boundaries into the interior of the metal, meaning surface corrosion gradually becomes structural damage. Medieval wrought iron behaved differently because of its internal structure. During forging, the slag trapped within the iron was stretched into long, thin fibres aligned with the direction of hammering. These slag stringers formed microscopic barriers distributed throughout the metal. When corrosion began, it encountered these barriers and was forced to spread laterally rather than penetrating deeper. Instead of destroying the metal, the corrosion stabilized into a dense protective patina. Wrought iron behaves differently because of its internal structure. During forging, the smith repeatedly hammered the iron while it was hot. This action stretched the trapped slag into long, thin threads, distributed throughout the metal. Under magnification, wrought iron resembles wood grain, with countless microscopic glass fibers running through an iron matrix. When corrosion begins in wrought iron, it encounters these slag stringers. The corrosion path is interrupted. Instead of penetrating deeper, it spreads laterally. Rust flattens rather than drills. The result is a stable surface patina rather than progressive internal decay. The impurities act as internal barriers. This alone would be significant, but medieval iron had an additional, unintentional advantage: phosphorus. Medieval smiths did not understand elemental chemistry. They did not know what phosphorus was. What they did know was which sources of ore produced iron that lasted. In marshy regions across Europe, iron ore formed naturally in bogs. This bog iron could be collected with minimal excavation. It also contained elevated levels of phosphorus. When smelted, that phosphorus remained in the metal. Over long periods of exposure, phosphorus promoted the formation of a dense and stable oxide layer on the surface of the iron. This layer limited the diffusion of oxygen and moisture. Once established, corrosion slowed dramatically. This effect is visible in one of the clearest surviving examples of ancient ironwork. the Iron Pillar of Delhi. It stands over 1,600 years old, weighs several tons, and has remained largely free from corrosion despite constant exposure to the elements. Modern analysis showed that its high phosphorus content, combined with slow atmospheric oxidation, produced a protective surface layer that effectively halted further rusting. Medieval European wrought iron achieved the same effect on a smaller scale whenever phosphorus-rich ore was used. Similar patterns appeared globally. Certain regions became known for exceptional iron, not solely because of superior skill, but because of geological composition. Iron produced near Toledo contained trace amounts of nickel and chromium, elements that improve corrosion resistance. In southern India, crucible steel known as woots developed unique internal microstructures due to slow cooling and trace elements present in the ore. These characteristics were not intentional in a modern sense, but they were repeatable. Trade routes emerged around material quality. Iron blooms from Sweden commanded high prices in England. Indian steel travelled long distances to Damascus for forging. Across cultures, the principle remained consistent. Preserving beneficial impurities produced materials with properties purity could not provide. The furnace responsible for this was the bloomery. Structurally simple but chemically important, a vertical shaft of clay and stone charged with layers of charcoal and iron ore. Air was forced in through bellows. Temperatures reached roughly 1200 degrees Celsius, hot enough to chemically reduce iron oxide, not hot enough to melt iron itself. This distinction is critical. Iron remained solid. Metallic particles formed and accumulated while molten slag drained away. What remained at the bottom of the furnace was a spongy mass called a bloom, composed of iron, slag, and uneven carbon distribution. Modern steel production melts iron completely. Slag is removed as liquid waste. The resulting metal is uniform and predictable. This increases efficiency and scale, but it eliminates internal structure. The bloomery process preserved it. The smith reheated the bloom repeatedly and worked it under the hammer. This was not primarily shaping, it was consolidation. Each hammer blow welded iron particles together. Reheating allowed carbon to redistribute. Slag compressed into aligned fibres. Internal voids closed. Residual stresses diminished. The metal improved structurally with each cycle. This process required time. An axe head could take days. Modern production stamps the same shape in minutes. Speed was chosen, permanence was not. That choice mattered economically. Medieval tools were not inexpensive goods. An axe could represent weeks of wages. A sword could represent months. These were not disposable items. They were assets. They were inherited, maintained. Failure had consequences. A broken agricultural tool could jeopardize a harvest. A failed weapon could be fatal. Quality was not optional. Guild systems enforced this reality. Apprentices trained for years before advancing. Poor workmanship carried professional consequences. A smith expelled from a guild lost the legal right to sell. Reputation mattered more than volume. In contrast, a modern tool that rusts out in 2 years imposes no penalty on its maker. Replacement is expected. The incentive structure has inverted. Maintenance practices reinforce durability. Finished tools were often heated and rubbed with oil or fat while still hot. The oil polymerized on contact, forming a bonded protective layer. This is the same principle used today to season cast iron cookware. Regular use further stabilized the surface. A dark magnetite patina formed, which is dense and protective. Tools stored dry and used frequently retained this layer. We did not abandon these practices because they failed. We abandoned them because they required ongoing care. The bloomery also enabled composite construction. The bloom contained iron with varying carbon levels. Skilled smiths identified these differences by spark patterns and behavior under the hammer. Higher carbon pieces were reserved for cutting edges. Lower carbon wrought iron formed the body. Forge welding combined them into a single tool. Hard where sharpness mattered. Tough where impact occurred. Pattern welding added additional interfaces. These interfaces increased internal boundaries where slag fibers accumulated, further interrupting corrosion pathways. The blade functioned as a system rather than a single compromised material. Even medieval quenching practices, often dismissed as superstition, had practical foundations. Many substances failed to harden steel effectively. Blood cooled too slowly. Milk performed poorly. However, brine and urine worked reliably. The reason is chemical, not mystical. Dissolved salts disrupt the insulating steam layer that forms during quenching, allowing faster heat extraction. The smiths did not understand the physics, but they observed the outcome. Practical knowledge was preserved through memorable language and guarded transmission. Tempering followed hardening. Polished steel was reheated gently until oxide colours appeared on the surface. Each colour corresponded to a specific temperature range and mechanical property. The smith selected the colour appropriate to the tool's function, then quenched to lock in that structure. This method remains valid today. It was developed through observation, repetition, and correction. By modern standards, medieval iron was inconsistent, impure, and inefficient to produce. Yet tools forged centuries ago still function, not in spite of their imperfections, but because of how those imperfections were distributed and controlled. Slag acted as internal reinforcement. Phosphorus acted as corrosion resistance. Solid-state processing preserved microstructure. These properties cannot be recreated once iron is fully melted. This knowledge was not lost accidentally. It was abandoned deliberately. Production goals changed. Quantity replaced longevity. Convenience replaced durability. The medieval blacksmith did not dominate material behaviour. He worked within it. He observed how iron responded and adapted his methods accordingly. Every rusted fence post, every disposable tool, every short-lived product reflects that decision. Progress is not automatic. It follows incentives, and incentives determine outcomes.